Thanks for the opportunity to speak here about one of my favorite subjects. It's also a pleasure to be here at IAS and in these beautiful surroundings, especially to a Dutchman. Of course, these surroundings here are very welcoming. There are streets called after our royal family, and there are places called Dutch Neck and the Harlingen Historical Society. That being said, I'm not entirely sure how much longer the Netherlands will be a monarchy, but that's maybe something to discuss afterwards. Okay, so this is about Noetherianity up to symmetry. Noetherianity is a property of modules, rings, and topological spaces. And in this talk, these will be modules, rings, and topological spaces on which a group acts. And Noetherianity is not going to be literally Noetherianity, but only Noetherianity for submodules, ideals, and closed subsets that are stable under this group action. But before I get there, let me mention a few motivating questions. At least for me, they were motivating. Why you might be interested in this topic. So the first question that actually got me started in this area is a question in algebraic statistics. So there was a question by Burton, who is a statistician, and Sturmfels, who is a commutative algebraist, and Seth Sullivan. So they were studying something that they called the Gaussian two-factor model. What is it? Is well, it's denoted, let's say, F2, n. And these are the set of all matrices of the form S times S transpose plus a diagonal. Let me say A1 up to AN, where S is an n times 2 matrix, and A1 up to AN are non-negative numbers. So why would you be interested in studying this set of matrices? Well, this is the set of covariance matrices of n jointly Gaussian random variables that you can express as linear combinations of two random variables plus independent noise on the n random variables. Yeah, so you might think that maybe there's two types of intelligence, and there's n questions on a test, and then at least approximately the performance of a random person on this test is going to follow this distribution. Okay. So the two hidden random variables are how intelligent, how they score on those two types of intelligence, and then there's noise for the individual questions. Okay. Anyway, but so this is a set of positive definite matrices, non-negative definite matrices. And the question they asked was of a very algebraic nature. So they asked, what are the algebraic relations among the entries of that matrix? We call that matrix sigma. Okay, so well, there are some obvious equations, namely sigma ij is equal to sigma ji, because it's a symmetric matrix. And then when you think a little bit harder, you see that if you look outside the diagonal here, then this matrix looks like a rank 2 matrix. So that means all the 3 by 3 determinants are 0. Yeah, so I'll call that 3 by 3 off diagonal determinants. And it turns out that this is not enough, because these 3 by 3 determinants that don't touch the diagonal only appear when n is at least 6. And for n is 5, there is already one equation, which they called the pentad. So, and this is 1 over 10 it's kind of irrelevant, but I'll explain where it comes from. And then the sum over all of the symmetric group on 5 letters, and then the sign of pi. So it looks like a determinant, but then it looks a little bit different, namely sigma pi 1 pi 2, and then sigma pi 2 pi 3, and so on, and sigma pi 5 pi 1. That's a polynomial, and the 1 over 10 is just to make sure that the coefficients are 1 rather than 10. So that's a polynomial that turns out to vanish on all the off-diagonal entries of this 5 by 5 matrix. And the question they ask is, do these generate? Right. All relations for n at least 6, well, at least 5. Okay, so by these I mean that, well, of course you can you can choose any 5 columns and then the same rows, and then you have a pentat equation. And so the question is whether the ideal of all algebraic relations among the entries of this matrix are generated, whether that ideal is generated by these guys. Okay. So that's the first, that's the question that actually got me started, and I'll say something about it towards the end.
What's the relevance of the real numbers in the
Nothing. Yeah, I could have written complex numbers here, but in statistics, it is a matrix like this. And so you can, it's a good point. You can ask variants of this question where you actually have a positive semi-definite matrix, and you look at so whether also the inequalities are somehow inherited. And well, Turton has a theorem to that effect, but I'm going to speak only about algebra.
So when you say off diagonal, because there will be a diagonal in S times S transpose as well. So are you taking diagonal? No, are you taking determinant of just the first part?
No, I'm taking, well, the point is outside the diagonal of this matrix, it is the same matrix as this. And so it has rank, so all the 3 by 3 determinants are 0. Yeah, because I'm adding only the things on the diagonal. So by off diagonal, I just mean you take 3 rows and 3 different columns. So there's no intersections between. Yeah, so you don't get get diagonal. Exactly, you don't touch the diagonal. Okay. So here's a different sounding question. So suppose I take any finite subset of the complex numbers, and I'm looking at let's say m comma k, and that's going to be the set of all matrices A in S to the n times n. So I only take entries in this finite subset, and let's assume symmetric. It's not so important, but let's assume symmetric. And the rank of k, and the rank of A is equal to k. Yeah, so that's some finite set. And now you might want to count how many elements this set has. And well, the natural way to count this is to realize that the symmetric group on n letters acts here by simultaneous row and column permutation. And so the question is, what can we say about the number of elements of n comma k modulo the symmetric group? So the number of orbits. Can we say anything about this? And especially, we want to do this for k fixed and n large. Okay, so how does this number behave for large? Okay, so maybe this is algebraic combinatorics, if that is great statistics. Okay, then there's a topic that I know least about, but it should be mentioned in these kind of talks because it motivated some of the theory that I'll mentioned later. Sorry, just copying what's written here. Algebraic topology. So in algebraic topology, you can ask questions like the following. You take a manifold, and maybe it has to be compact and oriented. Let's say connected. And now there are these spaces that people call configuration spaces, and this the spaces I'll look at are the so-called pure configuration spaces. So they are the set of injective maps from the numbers 1 up to n into n. Okay. That itself is a manifold, so it's you take the n-fold product, a Cartesian product of n with itself, and you remove the big diagonal. That itself is a manifold, and you can ask how does cohomology of this manifold behave? So, for instance, if I fix, let's say I fix an I, what happens? What happens with cohomology of this configuration space? Yeah, I guess I should call it M here, say with coefficients in Q for n sufficiently large. So can you say anything sensible about this? And well, the last example or kind of motivating question that I'd like to mention is this guy. So let's say algebraic geometry. So if you look at the Grassmannian of k-dimensional spaces of a vector space V, let's say of the complex numbers, then this lives in the projective space of the kth exterior power of V. And it is well known that this is defined by polynomials of degree 2 in here. Yeah, they are the so-called Plücker relations. And so just to mention one, they look like this. So x1, 2, x3, 4 minus x1, 3, x2, 4 plus x1, 4, x2, 3 is equal to 0. Okay. Okay. And so these equations, they're all of degree 2, regardless of whether of the dimension of W and the number K. And so you can ask questions like, suppose that I'm interested in other varieties living in this space, for instance, constructed from the Grassmannian. So one construction that people in algebraic geometry study a lot is the so-called secant variety. So that's denoted sigma r of grk comma v. This is just the following thing. You take r points in the Grassmannian, and then you take their span, and then you take the union of these spans and you take the closure. And so you can ask, is sigma r grk comma v for fixed r defined by polynomials of bounded degree. Say as k and v vary. Okay. So you see in all of these examples, you study some finite dimensional objects, and there is some parameter n that is allowed to vary, and in this last case also this other parameter k is allowed to vary. Okay, so well, these are the kind of questions that we can answer using Noetherianity up to symmetry. So just let me just recall what Noetherianity means. So R is, let's say, a ring with commutative with 1, and M is an R module, and X is a topological space. And then, M is Noetherian. That means that every chain M1, M2 of our submodules stabilizes. And R is Noetherian if, let me just spell it out, every chain I1, I2 of ideals stabilizes. And finally, X is Noetherian if and only if, by definition, every decreasing chain of closed subsets stabilizes.
So ideal is two-sided ideal?
Yeah, R is just a commutative ring with 1. So it's there. But you were right. Of course, we can study versions of also Noetherianity up to symmetry, and it has been done for certain non-commutative rings. But your R is just okay. And so now, suppose that you have a group acting. So there's a group, and it acts on R via automorphisms of rings, of this ring R, and it, let's say it acts on M. Oh, yeah, this is actually not quite what I want. Just do I want to see? M is a different ring. M is an S module. So in the definition, I will give this. There will be no action of the group on the ring. So G acts on R, G acts on M by S module automorphisms, and let's say it acts on X by means of homeomorphisms. And then M is called Noetherian, let's say G Noetherian, if and only if every chain of G stable.
Sorry, what kind of group is G? Any finite group?
Right now it can be any group, and it's going to be infinite groups. So it's going to be, in all the examples, it's going to be either the infinite symmetric group or the infinite general linear group. But for the definition here, it doesn't matter. So if every chain of G stable submodules stabilizes, and then here we get the same thing. So it's G stable ideals, and here G stable closed subsets. Okay. And so I'd like to just mention some. So now you have this new notion, and you can try to translate classical theorems from commutative algebra to this setting. And some of those theorems are going to give answers to these questions over here. So we start with modules. So the classical theorem in commutative algebra says that if you have that if M is a module finitely generated over a Noetherian ring S, then it is Noetherian. And so here's a version of that that involves the infinite symmetric group, and that's a theorem due to Church-Ellenberg. And in this generality, also NACPO, which says that suppose S is a Noetherian ring, and M is an S module, and the infinite symmetric group, so this is the union over all n of sim n, acts on M by S module automorphisms. And then we need a condition on the type of action. A kind of finitary action, so such that for M in M, there exists a W such that M is fixed by the symmetric group on W1, W plus 1, W plus 2, and so on. So I think of this W as the width of this element M. Right, so it's fixed by a very large subgroup of this infinite symmetric group. If M is generated by finitely many sim infinity orbits, is sim infinity Noetherian. Okay. Yeah. So that's what it is. So roughly speaking, a finitely generated object in this category of S modules with an action of sim infinity is itself Noetherian. That's what it says. Okay, so that's a statement. And there's a follow-up is that if kind of a consequence of this proof, if R is a field, then the dimension over R of Mn, now define in a moment what Mn is a polynomial in N for N sufficiently large. We say what this Mn is. So Mn is M and then sim n plus 1, n plus 2, and so on. Yeah, so it is those elements that have width at most n in the notion over there. So by definition, by assumption, M is the union over all M of Mn. Questions? So that's a statement about modules with an action of an infinite symmetric group. See how I'm doing on time. Okay. So now let me.
So R is S now.
Oh yeah, sorry. This is S. Yeah, you're right.
Yeah. The proof of this theorem give bounds for the polynomial when things kick in?
Well,
Say in this case of the field.
Well, it depends a bit how the thing is given to you, right? In what kind
of... But you can usually, I assume, compute P.
You can compute...
Given this kind of setup.
Yeah, so that's right. So essentially, the proof of this theorem, especially if S is a field, is actually quite easy. It's a kind of Gaussian elimination, but you have to do it in a clever way. And yeah, I'm not sure. I mean, certainly in the applications, they have bounds on where this happens, but in this general setup, I wouldn't know what is the correct statement. Okay, so then another classical, so this was about modules. Now about rings, the most classical theorem about Noetherian rings is Hilbert's basis theorem, and here's a version of Hilbert's basis theorem, again with the action of the infinite symmetric group. So this is due originally to Daniel Cohen, and then it was rediscovered by first by Aschenbrenner and Hiller, and then in a slightly more generality by Hiller and Sullivan, which is that so again, S is a Noetherian ring. There's no action of any group on S, and you look at the following ring. So you take S and then you add variables x11, x12, and so on, and then x21, x22, and so on up to some finite number, say xk1, xk2, and so on. And on this acts the group sim infinity. And the way it acts is just that pi xij is equal to xi pi j. And extending that to algebra, S-algebra automorphisms. And this is sim infinity Noetherian. Okay. Yeah. So what that means is that if you have any, well, an equivalent way of saying it is if you have any ideal in this ring that is stable under the infinite symmetric group, then it's actually generated by finitely many orbits of elements under this infinite symmetric group. Okay. So I think that's a very nice theorem. And again, the proof is not so difficult, especially when S is a field. It's a kind of, they actually show that every ideal has a kind of Gröbner basis, finite Gröbner basis. In fact, instead of acting with well, instead of acting with permutation, one acts with increasing maps from the natural numbers to the natural numbers, and that preserves certain monomial orders, and you can show that every ideal has a finite Gröbner basis. Okay. So that's the theorem about Noetherian rings. Now,
so is this equivalent to saying that the quotient, the GIT quotient?
What do you mean by a GIT quotient in this context? I mean,
you can take its spec.
Yeah, so it's nothing to do with the, I mean, there are no, you want to take the spec of the invariant subring? There are no invariants, right? Because any polynomial has finitely many things, and then if you act with a permutation, you get a different polynomial. So it's not about infinite series. There's no infinite symmetric functions or so. What you can do is take invariants under SLK acting by row operations here, and that's actually often a useful thing to do. And that ring of invariants is going to be again Noetherian, at least in the case where S is it's a field of characteristic zero, which you need things like Reynolds operator. So here's a nice theorem that we proved with Bob Egremont and Hazar Farouk, which is about this setting, namely, so suppose if we call this ring R, and then let's suppose that we take one of these ideals. So this I is a sim infinity stable ideal. And then, like in the case of this theorem over here, at every finite n, you get some object that behaves sufficiently regularly with n. So we can have that. So let's say Rn is just the same thing, but with j less than or equal to n. So it's this ring, but we just stopped the matrix of variables somewhere. And In is I intersected with Rn. Then you can look at the number of irreducible components of Rn modulo In. That's going to be an ideal in Rn. This is going to be an ideal here. Yeah, by irreducible components, I mean minimal primes. So maybe I should say spec of this. And this is an algebra. You can look at the topological space of all prime ideals. And that turns out to be a quasi-polynomial in n for n sufficiently large. A quasi-polynomial is like a polynomial, except that the coefficients are not constants, but depend on n modulo some fixed number. So, or in other words, it's a function for which there exists a sequence of polynomials, such that it's this polynomial if it's 0 mod m, and this polynomial if it's 1 mod m, and so on. So call it a quasi-polynomial.
I used to call it polynomial periodic.
Polynomial periodic. Okay. Yeah, I've heard polynomial on cosets or terms like this. But anyway, that's what it is. So things like n divided by 2 rounded downwards. That's a typical quasi. Okay. Then there's a remark that is that this example here, unfortunately, doesn't generalize beyond one index that goes to infinity. So rings like C, now I'm just specializing this S to say complex numbers, x1 up to xd, where 1 up to id are all natural numbers, and then with pi xi1 up to id is equal to x pi i1 up to pi id, they are not sim infinity Noetherian. For d at least 2. Yeah, so for d is 1, it's the special case of that where k is equal to 1, but for bigger d, they are not sim infinity Noetherian. However, they are Noetherian in some sense, in a weaker sense, and over a bigger group. So it is topologically Noetherian. Up to GL infinity. So GL infinity is the union over all GLN, let's say, of the complex numbers. So what I mean by this is that if you take any chain which which is a chain of sub varieties of this space of infinite by infinite by infinite blocks of numbers, tensors. If this chain, if these are GL infinities stable closed subsets, then it stabilizes. Yeah, and the way, so for D is 2, the action here is just by left multiplying with that matrix and by right multiplying with the transpose of that matrix, and similarly for bigger D.
Stronger statement for ideals false?
We don't know. So that's an open. And I think we already don't know for D is equal to 2. Although, for symmetric matrices, it's true, and for skew symmetric matrices, it's true. But for arbitrary matrices, I think we already don't know. Right. Okay, so very good. Okay, so let's go back to the question. So our first question was this thing about F2, n, which was this Gaussian two-factor model. Now that lives in, well, the way I said it, it lives in symmetric n by n matrices. And so, unfortunately, by this remark, this space is actually not Noetherian. So, or this ring is not Noetherian. So unfortunately, the ring, let's say, since we were working over R, let me call it like that, but it doesn't matter, sigma ij, and then modulo sigma ij minus sigma ji. And now I and j are allowed to take values, arbitrary natural numbers. This is not sim infinity Noetherian. However, we can do something like what Peter suggested, namely, we can compute. We can pretend it is Noetherian and try to compute a Gröbner basis. And if that computation terminates, then you have proved a theorem. And so that's what we did. So a theorem, one can eliminate, well, so by a Gröbner basis computation, which I'm happy to tell more about if you're interested, but by a Gröbner basis computation, which in 2000, so this is long ago, 2009 or something, it took maybe a weekend on all the computers in Eindhoven, at the university in Eindhoven. And then the answer to that question was yes. So answer to Durton, Sturmfels, and Sullivan is yes. So those pentats and off-diagonal determinants and sigma ij is equal to sigma ji, they generate all the algebraic relations. Now, of course, the next question is the 3-factor model and the 4-factor model and so on. And here we don't know, since this is not a Noetherian ring, we don't know whether there is such a finite list of equations. What we do know, however, is that topologically it's defined by finitely many equations. So there's a theorem which I didn't mention, which says that if you take a map, as sim infinity equivariant map from a space of this type into a space of the type that we're talking about over here, then the image is defined up to the symmetric group by finitely many equations, but only as a set. We don't know whether it's true for ideals. Okay. Right, and also this computation, I think even now, 13 years later, we cannot do for the 3-factor model. Right, okay, then we had this this other problem, namely counting matrices of a fixed rank with entries in a fixed finite set. So
There's no small dimensional, I mean, those theorems of stability, this you ran on a computer.
yeah,
There were no small dimensional differences to that problem. In other words, in the Sternfeld problem, maybe you said 6, something only kicked in at 6.
yeah, it started at 6, but for the Grosvenor basis stabilizes only at n equal 9. And so, and then to test that it is really a Grosvenor basis, you have to go to 18, 2 times 9. You have to look at all the different ways that you can embed two sets of 9 numbers in an increasing way in 18 numbers and check that all the S pairs vanish. It's a pretty big computation, which, okay, I should have mentioned, this computation was done not by me, but by Andres Bauer.
But for the K-factor model, you know which equation to expect. So you have the, I mean.
Well, there are the off-diagonal something determinants, and there's bound to be more. We don't know what they are in general. It could be very well that it always stabilizes at 2 times k, like 2 times k plus 1, like here 6 for 2. But we don't know that. Okay, then we had this set M k comma n sitting inside S to the n times n of rank k matrices. And we wanted to count their number of elements. And so what you can do is, so a priori, this seems to live in the wrong type of space again, because it's matrices, but you can look at something very similar to what happened here. Yeah, so we can look at C of, let's say, n times k into C to the n times n. So this is the map phi that sends a matrix A to A times A transposed. Is that right? Yeah. And then it turns out that the number, so this is obviously sim n equivariant. And so the number of irreducible components of phi inverse of m k comma n is equal to the number of m k comma n. Yeah. So in other words, this is a finite set, and its fiber is actually irreducible for every element in there. And the same is true when you mod out the symmetric group. And so by this theorem that we had over here, this is a quasi-polynomial in n. For n sufficiently large. I guess for k is equal to 1, it's a very easy exercise. For k is equal, and it's actually a polynomial, but for k is equal to 2, it's already a quasi-polynomial. There's some n divided by 2 rounding downwards in it.
What's the period as a function of k?
Sorry, what's that?
It's what I call polynomial periodic. What's the period as a function of k? You know?
Yeah, so no, I don't. I only know it for k is equal to 2, and then the period is 2. Provided, sorry, this is for S is just 0, 1 matrices. Then I know that.
Okay.
In general, already it's very complicated. Yeah. In general, I don't know. Okay. So that's that. Now, we had this HI, so that was the third topic, HI of the configuration space of endpoints, pure configuration space of endpoints on a manifold n with values in Q. Now, the way to put this into the framework that we're discussing here is that that there's a natural map that goes from conf n plus 1 n into conf conf nm, maybe just forgetting the last point. And then if you take cohomology, you get maps in the opposite direction. And so if I call this, and these maps are equivariant with respect to the smaller symmetric group. Yeah, because this map is equivariant with respect to Sn, sim n. So you get a map from Mn into Mn plus 1. And what essentially Church already proved, but then Church-Ellenberg and Farb proved in a slightly more general setting.
So what is Mn? Mn is the ith cohomology?
Yeah.
Mn.
Yeah. Yeah, sorry, I shouldn't have called that M.
Yeah.
Yeah, you're right. But I called my modules M before. Yeah, so let me call it N or something. But it's this cohomology. And so what they proved is that in the setting that I described, where M is compact and orientable, this sequence, or maybe it's better to say the union of it, this is one of those of the type in the first theorem. Yeah, so there's an action of the infinite symmetric group, and it is finitely generated. So that's the important point. Finitely generated. And so what that means is that you get a polynomial.
Embedded into N plus 1, is that clear?
It's certainly true for n little n sufficiently large. Yes. Maybe it's true for all n. I'm not 100% sure. Certainly true. Eventually, that's actually a general fact about these so-called FI modules that I didn't call like this, but this is a slightly more general definition than this, where you start with a module on which the infinite symmetric group acts. But for n sufficiently large, it's the same notion. So in particular, this means by their theorem that the dimension over Q of HI conf and Q is a polynomial n for n sufficiently large. Okay, so now we had these Grassmannians still to worry about and their secant varieties. No, this is a polynomial. So this is actually, so here was a quasi-polynomial in counting these irreducible components of these guys, but in FI modules, yeah, so in the theorem by Church-Ellenberg and Farb, it's really a polynomial. Okay, so the last part was this question about GRK V sitting inside V of wedge K V. And so if this guy has dimension n, then as I said in the beginning, there's two parameters to play with here. You can play with little n, or you can play, and you can play with little k, and maybe with both of them. If you only increase n, so for k fixed and n to infinity, this is not such an interesting case. Well, for one thing, it follows from this theorem over here that you get finitely many equations for any subvariety of wedge k of c to the n where n grows. So get finitely many equations for GR I think I called it sigma R GR K comma V. Yeah, and also R is fixed. Okay, and by getting finitely many equations, I mean that they again that their orbits under the infinite general linear group define this this rth secant variety. As I said, again, we don't know. Well, in this case, actually, yeah, I guess in this case we also know that that at roughly speaking r times the dimension of v, you get all ideal theoretic equations. So this is one thing, but now, what about letting both k and n go to infinity? And then it's actually better to let k and n minus k go to infinity. So k n minus k both to infinity. What can you do in this case? Well, so there's this object called wedge infinity over 2 of, let's say, c to the infinity. And I'm not going to give a precise definition here, but essentially it is, you take the wedge of, let's say, k of c to the n, and let both of these go to infinity, and take the union of all of these spaces in a natural way, in a way that where in both cases you go to infinity. And so you can think of this as a space spanned by let's say xi1, wedge xi2, wedge, etc., where I1 and I2 and so on are all elements in the integers, and ik is equal to k for all k sufficiently large. But the k may vary among the different expressions like this. So these are like, well, infinite wedge products of basis vectors. Okay. So this space is called the infinite wedge. And inside it, or rather in the dual, so we give a theorem. So if you should think of this as the space of Klucker coordinates, and then the dual space is the space where geometry happens, and so this is GL infinity Noetherian. And I should really say GLZ here, because here the basis vectors are kind of labeled by all integers, not just natural numbers.
So see, you're taking ik equals k.
Yeah, so one
It will all become 1, 2, 3, 4, 5 because
no, because these are integers. So you can have negative numbers. You have a bunch of negative numbers, and then from some point on, it equals your sequence.
Okay.
So it's a countable set of coordinates. Exactly. And so this is a very nice theorem, which in this form is due to Ilya Nekrasov, who is a student of Andrew Snowden, and it builds on work that Rob Egermont and I did in the past. And it implies that all varieties, like the Grassmannian, that kind of behave functorially in choice of the vector space and live in wedge something of this vector space, that all of these are defined, at least set theoretically, by finitely many equations up to this group.
PL is really appearing as a C module?
No, as a variety. So sorry, as a variety, as a topological space. Yeah, thanks for pointing that out. So I think of so these are my coordinates, and so it's a countable set of coordinates, and then I look at the topological space, which is this with the Zariski topology giving right those coordinates. Yeah. Right. Otherwise, it wouldn't say anything about that. Right. I mean, also as a well. So now I think I have a few more minutes left. Let me finish with my favorite conjecture in this area, which is that if you look at the infinite Grassmannian, which lives in kind of C to the infinity star, and so this lives in this space over here, H infinity over 2 of C infinity star. This is actually in Z topologically Noetherian. Okay. This is a different statement from this one over here. Let me explain the differences. Here's a very large space on which a very large group X, and it is Noetherian. Here's a much smaller subvariety, just a Grassmannian. This is just one orbit under this, or the closure of an orbit or something. Maybe just one orbit. Okay, I always get confused. It's essentially one orbit under this group, but now there's a much smaller group, and so the conjecture is that this is Noetherian. And like to say why this is my favorite conjecture. This would actually imply things like the graph minor theorem and the matroid minor theorem, if you do this over other fields than the complex numbers. So if someone would find a short proof of this statement, that would get rid of 700 pages of complicated graph theory.
You mean Seymour Robertson theorem?
Yeah, exactly.
So what is Symmetry? Sorry.
All permutations of the integers. So needless to say, I have no idea. It doesn't matter here whether you take all permutations or just finitary permutations, because actually it does matter. Finitary permutations. Sorry, yeah, finitary permutations, because you have to preserve this kind of condition that we have. Of course, I have no idea how to prove this conjecture, so but if anyone is looking for a fun problem, there it is. Okay, thanks.
Are there any more questions?
So this is space, this Grassmannian embedded there. Is that this?
It is Santos Grassmannian.
Isn't it the infinite Grassmannian?
Yeah.
Embedded by the boson.
Yeah, that's it. Boson or I always forget.
Boson or fermion, I always confuse.
Exactly. Fermion is probably this one, right?
Yeah,
where you have wedge.
Yeah,
I think fermion is skew symmetric. Yeah, but it's the one where you have a wedge.
So that's the standard representation with respect to one of those boson or fermion.
Right. It is exactly that. So I've tried translating this to the other representation and seeing what it means there, but it didn't help me.
But one knows, I mean, as a variety, one knows exactly what the relations are. Right. Very precise relations.
Yeah,
like the Plucker
relations. Yeah, exactly.
Relation coming from the Casimir operator.
Yeah.
And
yeah. So we know. So exactly. We know all the equations for this variety, but this group is very small, and so what you have to do is, well, you start with some variety inside this Grassmannian. It's defined by some new equations that do not follow from the Plucker relations. Then, of course, using the Plucker relations, you can put it in some standard form or something, using this, what's called straightening laws or something. But then what? So then when you act with, kind of increasing maps or decreasing maps or something, then that preserves these straightening laws. So you still have something that is in standard form, but as soon as you start permuting things become messy.
Symmetry just acts in the standard way, just by permuting the.
Yeah, just by permuting these. Those basis elements. Yeah, so if you would permute I1 and I2, you would get minus that base, coordinate over there.
then the Grassmannian application, it's certainly not equivalent. It's just one orbit. I mean, this is a much more general statement.
Yeah.
It's a much more general action.
This is really a kind of, so if you replace C by a finite field, then this is the Matroid minor theorem.
Okay.
And then it's actually a theorem people claim, but there is no proof in the literature. So it was claimed to be a theorem, and there's kind of expository papers, but not yet, as far as I know, not yet a complete proof.
All right. If there are any more questions, let's thank Jan for an excellent